Suppose I had two conductors separated some distance from each other, and I gave them different charges, one positive and one negative, as I've drawn here. You would expect there to be field lines going in between the two, and in that case you would also expect there to be some sort of potential difference between these two charges. And also, for simplicity, let's assume they both have the same charge but of opposite sign. So one is positive, the other is negative Q. So there's some things that we could think about here. The potential difference between them would have some relation to the charges involved, but it might also depend on the materials involved, how the charges are distributed, things like that that could affect the affect the ratio between the charge here and the potential. So we're going to introduce a concept of this will be a ratio between the charge on one of the conductors and the potential difference between those two conductors. And a way of referring to this then is saying there is some sort of potential between these two conductors, and it's going to have some capacity to hold charges there. This is where then we're getting this term of capacitance. So the capacitance is simply then defined as the charge on the conductor and the potential difference between those two conductors. And this is going to have units of what we call farads, capital F, named after Michael Faraday. And so this ratio might seem not too interesting, but there's going to be some differences depending on, again, the separation between the charges, the distribution of the charges, and then, of course, the potential difference. If I were to hook up a couple of conductors to a set of batteries, then using that, I can affect the voltage difference across, the potential difference across, and in that way I can then basically charge up those conductors and see how much I could stuff onto there. The most common sort of conductor or capacitor that you would usually think of is two parallel plates with each other. They all again have some charge Q on each of them, plus and minus for each plate. They're separated some distance apart, and they'll also have a certain surface area. So the plate might look something like this, and will have some surface area A. Now, there will be some definite amount of potential difference between these two. So to figure that out, we would first want to consider what's the electric field from a plate. That is determined earlier that from any one plate, or one surface like that, the electric field from it will be the charge density divided by 2 epsilon naught. And the charge density sigma is the surface charge density. And since we have two plates, the electric fields are going to basically add up, and so the real electric field we'll have, and this will be the electric field between the two plates, will be sigma over epsilon naught, and sigma is defined as the charge on the plate divided by that surface area. So the potential difference then is going to be related to the electric field and over what distance a charge would move over that. So that'll just be the distance between the two plates. So if I were to imagine I had some positive test charge here on plate positive Q, it would move towards negative Q and it would pick up some energy that way. That's the sort of potential then we would have. The charge would move along that way and be accelerated by the electric field. And the bigger the distance is across, then the more it would get accelerated. So we'd see why it would have this nice direct relationship. So let's plug in for the electric field in between the two, and we see that that should be QD over epsilon naught A. So if we then take our definition of capacitance as Q over delta V, the potential difference, we can plug in what we had just found here, and we find then that the capacitance, when all the terms nicely cancel out, as epsilon naught A divided by D. So epsilon naught is a property of the vacuum between the two plates, A is how big the plates are, and D is their separation. So make the separation smaller and smaller, then you can have more capacitance. What would that mean? It means with the the same amount of potential difference, you can get more charged stuffed onto there. And with bigger A, there's more capacitance, which makes sense because bigger surface area, more space to put charges for the same potential difference across them. Now there will be certain limits for engineering points, for example, that if you put the plates too close, then you can imagine that charges could start zapping across through the air in the same way if you build up a charge on your body and you get close to a doorknob, you zap across. So you wouldn't normally just put the plates as close together each other until they're like a proton distance apart. You would expect then energy to start zapping across earlier. And this epsilon naught then, like I say, is a property of the vacuum, and that's assuming that we have nothing in between these two spaces. But one of the things we can also do is put in another substance that would have a different value. So epsilon naught is for the vacuum, and if we instead use what we call dielectric materials, that will in fact actually affect the capacitance, because most materials will have a epsilon value instead that would be larger than the epsilon naught value. So what does this really mean physically? It's basically saying how the material is going to produce its own sort of electric field inside of it when there's a potential going across it, and that will affect the total capacitance of the system. We won't get too much into the material science aspect of why this is, but it's an engineering point that you don't want to just depend simply on the materials that you have and nothing between them. Otherwise, if you want a large capacitor, you need a huge area, or a very small d having the problems of zapping across the two plates. Big A has the problem of very hard to fit into your iPhone if you want to put some sort of capacitor into there. Obviously, if you want a large capacitance, a very large A would then become a bit problematic. The last thing to consider is that there's also going to be some amount of energy stored into here. You can imagine if you have some sort of charge here on this plate and it was to move over to this plate, then it would pick up some amount of kinetic energy. There'd be some potential energy difference across. So we want to consider that sort of thing. So if we wanted to consider, just some rather little tiny bit of charge, so we want to look at, say, a tiny little bit of charge, and there's an infinitesimal amount of work being done, and we remember that that's going to be related to the change in potential energy, that small amount, and since we know the relationship between potential and potential energy, this would be then that potential difference and that tiny little bit of charge we have in this case. And from our definition of capacitance, we could then rewrite this as Q over C dQ. So if we want to find the total work, that's then just taking the integral over that little bit, Q over C dQ, and we'd be moving all the charges, so from no charge to the total amount of charge across there, and we would find then that the work would just be Q squared over 2 times that capacitance. So in that case, we can talk about the potential energy stored up in a capacitor. In that case, the potential energy would be simply equal to Q squared over 2 times the capacitance of any capacitor we have, but the parallel plate capacitor is the simplest example. And from the capacitance equation, what it means, we could also then rearrange that as 1/2 the charge times delta V, or we could have that as 1/2 the capacitance times delta V squared. So in particular, this expression would make sense to us. With more charge, there'd be more potential energy. With a larger potential between the two, there'd be more energy. And then these other two are ultimately equivalent just from the definition of capacitance. So we can now talk about storing not just charges on a capacitor, but also energy into a capacitor. And once we begin talking about circuitry, we can then start talking about charging things up and releasing energy into a circuit system using capacitors or collections of capacitors.